to sum up things, whatever we have learned. So first we started with Huygens theory, that is we started with wavefronts. So wavefront is basically the disturbance in the medium caused by the vibration of waves, correct? Then we learnt about different types of wavefronts. Under that, three main things. One is a spherical wavefront where the source is a point object. Then we have cylindrical wavefronts, and then we have planar wavefronts. So planar wavefronts is if the source is at infinity, correct? So these were the types of wavefronts what we learned. Then we learned about reflection and diffraction by wave theory, correct? Then we moved on to interference. So we learned about how interference happens. So interference is basically superposition of waves. Since superposition is happening, so we have either constructive interference or destructive interference. Depends on how the waves look like, correct? So if we have constructive interference or a bright fringe, then the path difference has to be n times lambda, because if you have 1 lambda, 2 lambda, 3 lambda, everything is constructive, right? Then for a destructive interference or a dark fringe, the path difference has to be 2n plus 1 into lambda by 2. In other words, an odd multiple of lambda, right? So if you have 1 lambda, one whole wavelength, then if half of that wavelength gets added up to one whole thing, then we are going to get a destructive wave, correct? So destructive interference or a dark fringe. So this was the path difference for the dark fringe and the bright fringe, correct? Then we moved on to how the intensity will work out, right? So for intensity, we have I is equal to a1 square plus a2 square plus 2a1 a2 cos theta, correct? So if cos theta is 0, then we have a1 square plus a2 square plus 2a1 a2, right? Which is nothing but a1 plus a2 whole square. So the maximum intensity is a1 plus a2 whole square. Then minimum intensity will be a1 minus a2 whole square, correct? So if you take the ratio, we have I max divided by I minimum is equal to a1 plus a2 whole square by a1 minus a2 whole square, right? Then we also have the width, that is the width of the slit, and the intensity, how they are related. So we have W1 by W2 is equal to I1 by I2 is equal to A1 square divided by A2 square, okay? So the width and the amplitude, that's how they are related, right? Next, we actually moved on to how to figure out the fringe width, correct? Now, to find the fringe width, what we actually did was we figured out the position of the nth bright fringe or the nth dark fringe, and then we did it, correct? So we got y is equal to n lambda d divided by d. This is for the nth bright fringe, correct? Then for the nth dark fringe, we have y is equal to 2n plus 1 into d lambda divided by 2d, right? So this for the dark fringe. Now to figure out the fringe width, we have beta is equal to lambda d by d. Now how we got this is you subtract the distance of the nth bright fringe and the n minus 1th bright fringe, or nth dark fringe, n minus 1th dark fringe, right? So this is the fringe width beta, which is lambda d by d. Now we also have the angular width of the fringe, which is given by theta is equal to lambda divided by d, right? So this is what we got. So what we can conclude is in interference, beta is proportional to lambda. That means more the wavelength, bigger is the fringe width. Lesser the wavelength, smaller is the fringe width. And beta is proportional to d, meaning the more distance you have between the slit and the screen, the fringe width is going to be bigger. Then beta is inversely proportional to d. That is, if the fringe width is very, very close, then the slit width is very, very close, then the fringe width will be very, very big, okay, or vice versa, right? So this is what we saw in interference, right? So then we moved on to diffraction. So in diffraction, we had two things, Fresnel and Fraunhofer diffraction, correct? So in Fresnel diffraction, what we had was the source of light is at a finite distance from the slit, and for Fraunhofer, the source of light was at infinite distance, meaning the wavefront was a planar wavefront. Right? In diffraction pattern, what we have is the central maximum and then all the series of first secondary maxima, second secondary maxima, first secondary minima used to come. Right? So for maxima, we have sine theta is equal to n lambda divided by a. Now the distance of the nth bright fringe was given by yn is equal to n d lambda divided by a, correct? So beta will get it as d lambda divided by a. So what we figured from this was all the secondary bright maximum or the tertiary bright maximum, all of them are of the same width, correct? So this is what we got. Now similar way for a dark fringe also, right? So for a dark fringe we had 2n plus 1 into d lambda divided by 2a. Here also beta was nothing but d lambda by a. Now we did all these things. Now the most important part was the central maximum. So central maximum was given by beta naught is equal to 2d lambda divided by a, because it's twice the size, correct? Right? So we saw how diffraction works. Then we saw the limit of resolution and resolving power, correct? So resolving power was what? So the distance or the two objects, if they are very close to each other, how well you can distinguish between these two. So we had Rayleigh's criterion for resolving power, correct? Then using that Rayleigh's criterion for resolving power, we did the same thing for a microscope and a telescope. Now the limit of resolution for a microscope was 1.22 lambda divided by 2 mu sine theta, right? So the resolving power would be 1 over d is equal to 2 mu sine theta divided by 1.22 lambda. So this is the reason why oil immersion microscopes we use, because mu value is a little more, and we also use lambda value to be very less. This is the reason why electron microscopes, they have very high resolving power, because lambda is very less, right? This is for a microscope. Similarly, we did it for a telescope, right? So the distance between the two binary stars, if they are very close, how we can figure out that there are two stars rather than one? So we have limit of resolution to be theta is equal to 1.22 lambda divided by d, or resolving power is 1 over theta is equal to d divided by 1.22 lambda. So bigger the aperture we have for the telescope, more will be the resolving power. This is what we learned in diffraction, right? Then we moved on to polarization. So in polarization, we learned what is a polarizer, what is an analyzer, and how a plane polarized light will come from an analyzer, correct? Now, after that, we learned about how polarization can be done. One is by scattering, another one is by reflection, correct? So when we learned about polarization by reflection, we also learned about Brewster's law, which gave us the relation between polarizing angle and the refractive index of the medium, which is mu is equal to tan p, right? Then we also used Snell's law and Brewster's law to figure out the relation, which is r plus p is equal to 90 degree, meaning the incident ray, the reflected ray, and the refracted ray, all three are perpendicular to each other. Okay, so we have the angle between the reflected ray and the refracted ray is also 90 degree. So this is what we learned then. Then we moved on to Malus law, that is to find the relation between the intensity and the angle between polarizer and analyzer, which is I is equal to I naught cos square theta, right? Now one more important point which we have to notice here is, if only polarizer is present, then remember the intensity will reduce by half, okay? Meaning if you have just the polarizer and unpolarized light is incidenting on it, then the intensity of the plane polarized light will be half the intensity of the unpolarized light, which is nothing but I naught divided by 2, right? So this is all what we learned in wave optics. So wave optics is quite an important chapter. So make sure you are thorough with interference, diffraction, and even parts of polarization.